So, this lecture we will be discussing about the various instabilities that can occur during the sheet metal forming. So, the first one as we have discussed earlier, so that is so if you write that load instability and tearing. So, let us see that the instability of the sheet to transmit the required force, that is what so that is what when you are transmitting the load, at some stage an instability sets in and the metal finally end up in tearing, okay, or any other type of defect which can happen. See, if you are considering the case of a deep drawing process where your material is like this, it is being drawn and maybe the punch was here, okay, and your die, this is your die. At this wall region, you will find that the force required, see, two things are happening. One is the metal will have to, because you are holding here and the metal will have to be drawn inside from this side, and here another is that here the strain has to take place, tensile straining will be taking place on the side walls. So, if the force required to draw the flange inward, if this force is, it exceeds the strength of the cup wall, then what will happen is that it can fail there. Okay. So, this will happen when the tension around this circumference reaches a maximum and will be seen as a maximum punch force. So, that is what happens. So, when the load reaches the maximum value, what will happen is that at this region the failure will take place. Okay. So, deformation becomes concentrated at some diffused neck region, okay, and it is no longer uniform. At some specific area the deformation takes place, and this is called as the global instability. There are two things which are coming into picture. One is the diffuse neck and the local necking. These two things are going to happen. So, if you take a cylindrical piece which is loaded in tension, suppose this was a cylindrical piece, a tensile sample, and when you are loading it, after reaching the maximum value, you will find a necking which is taking place over this area. So, the total diameter gets reduced. Okay. So, similarly, so if this is the cylindrical piece, similarly if you take a rectangular piece, a flat specimen, generally which is used for sheet metal operations, okay, where this is your thickness. What you will find is that at some stage similar to this, you will find that okay, let me just draw like this. So, at some stage you may find that okay, similar to here you will find a decrease in the width. This is called as the diffused necking. Whereas, in addition to that, no, you may find here which is called as this is like deformation taking place along very thin narrow band, okay, like in metallurgical terms, no, you call it as loader bands. So, this is called as the local necking. So, this diffused necking may end up with a local necking. So, that in sheet metal operation. So, that is, these are the two differences, this is the diffuse necking and this is the local necking. So, this one should understand what is happening. Okay. So, in a diffuse neck once it happens, now this is like a global instability criteria which is going to take place. So, we can just look at how this failure takes place is, one is due to this diffuse necking, which is a global necking, global instability criteria. So, second is the localized necking. So, when this happens in any localized area, when this happens over a narrow band, this will rapidly lead to tearing of the material, and the failure will terminate there, and that failure will terminate the forming process. Okay. So, this is just a local instability criteria. And another type of failure is your fracture. When you are deforming the material, it gets work hardened. When it work hardens, it gets brittle, and at some stage you will find that the material just fails in a brittle way. So, that is called as the fracture mode. Okay. So, and another type of instability is wrinkling. So, this is when one of the principal stresses in any element is compressive, then what happens? The sheet may buckle or it may wrinkle. That means its thickness will get increased. This is a compressive instability and resembles the buckling of a column. So, that is what. So, the normal failure in sheet metal operation is instability which takes place is by any of these, or it can be a combination of all. So, but mostly it will be any one of these only. Okay. So, now when we have to look at it, let us take one by one. So, what are the theories behind this localized necking and diffused necking? Let us consider a uniaxial tension of a perfect crystal, perfect strip. So, if you have a strip like this, and you are applying your load over this area P, this is your length, this may be your width, and this is your thickness. Okay. So, if you just look at this in such a case, in a normal sheet metal operation, the type of stresses we can see that it is along this one we can call it as sigma 1, and along this direction sigma 2 is equal to 0, sigma 3 is also is equal to 0. This is the normal assumptions which we take it. So, we can always write that since the volume remains constant, say A into L is equal to A naught into L naught. This part which I am going to explain was discussed in the earlier class, but still I wanted to bring it here. Okay. So, that means you can just tell that from dA by A plus dL by L is equal to 0, or dL by L we can say is equal to d epsilon 1, okay, that is equal to minus dA by A. Okay. So, the load in the strip, the load in the strip P is always equal to sigma 1 into A. Say if you differentiate it, you can get it as dP is equal to d of sigma 1 into A, so is equal to 0, the maximum load. For the maximum load, this is the condition. Okay. So, if you just take that, that is dP by P is equal to d sigma 1 by sigma 1 plus dA by A is equal to 0 for the maximum condition for at the maximum load. Equation number 1. And for a strain hardening material which follows that sigma is equal to K epsilon 1 raised to n, which is the power law, we can substitute in this and we can get it as 1 by sigma 1 into, if you differentiate it. Okay. Differentiating, we will get it as 1 by sigma 1 into d sigma 1 by d epsilon 1 is equal to 1. Okay. Okay. this is a general equation. So, this is one relation we are getting. This is the equation 1. And for this particular case, if you just take it as 1 by sigma 1 into n k into epsilon raised to n minus 1 is equal to n by epsilon 1. So, we can get this equation number 2. These two cases we are getting. Okay. And if you substitute from 1 and 2, we can get 1 by sigma 1 into d sigma 1 by d epsilon 1 is equal to n by epsilon 1, that is equal to n. So, that means the strain at maximum load, which we have discussed earlier. So, the strain at maximum load for a perfect at maximum load for a perfect strip so that means we can say that this epsilon star is equal to n, because we have got that epsilon is equal to at maximum this one is equal to n, that was good. So, diffused necking cannot occur in one region, that is another thing. This diffuse necking cannot occur in one region. So, in a perfect crystal or a strip, the load to deform the strip, we can get it as P is equal to sigma 1 A. So, you can write it as sigma 1 is equal to k epsilon 1 raised to n, and A is equal to, because A into L is equal to A naught into L naught. So, we can say this A, we can write it as A naught L naught by L. So, that we can write it in this form as K A naught epsilon 1 raised to n L naught A naught into L naught by L naught by L1. So, we can write that it as exponential minus epsilon 1. Okay. Equation number 2, that is because since epsilon 1 is equal to, so log L by L naught. So, for the tension in a perfect crystal, you find that it is epsilon star is equal to n, and you are getting this relationship P is equal to k epsilon k A naught into epsilon 1 epsilon 1 raised to n into exponential minus epsilon 1. Now, let us take the case of a tension in an imperfect crystal. See, this tension in real material, it is never perfect. Even if you just assume that okay, it is well polished sample and other thing, even surface also is never perfect when you look at at a macroscopic level. But most of the sheet material, when you look at the microstructure, there are some imperfections inside. It can be voids, it can be very fine second phase precipitates, which will behave in a different way. So, you will find that no material is a perfect crystal. So, let us, for our analysis, let us assume a case where there is a small imperfection, and we assume that imperfection is due to the minimum reduced area, cross sectional area, where stress concentrations are taking place. Okay. So, if there is a void inside, okay, that means our effective cross sectional area at that section is less. Okay. So, that way we can just in a material let us introduce a small imperfection. See, basically if I just consider this as a material, let me just consider like this. Okay. So, this is an imperfection area, whereas here it is a perfect area. So, A1 sigma 1 and epsilon 1, and we are loading along this direction P in a tensile sample. we are assuming a tensile sample having a small imperfection. So, in this region, let us say that the A plus dA, A1 plus dA1, so sigma 1 plus d sigma 1 and epsilon 1 plus d epsilon 1, these are the conditions which are there. If you assume such a case, that means here a small reduction in area is there and you are applying a load P across this. The same load is transmitted through equally through the two sections. So, one is the section is the imperfection here and this is a perfect. It is not crystal, we can say, what is it called, strip, perfect strip, perfect strip. Okay, so we are having these two regions. One is a perfect strip where the cross section area is large. So, when this external load is applied along the, it is equally transmitted through this section A and B. Okay. So, in such a case, this equation 2 will become, we can write for the two cases. Equation 2 gives, so one is P is a constant. So, we wrote that K A naught into epsilon 1 raised to n into exponential minus epsilon 1. So, that is for this this perfect size. Now, that should be equal to whatever be the stress and strain and at the imperfection area. Okay. So, we can say the K is a constant for the material. So, we can say A naught plus d A naught into epsilon 1 plus d epsilon 1 raised to n into exponential minus of epsilon 1 plus d epsilon 1. Okay. We are getting this. Okay. Here it is not clear, I will write it. This is equal to K A naught plus d A naught, where d A naught is negative. Okay. Into epsilon 1 plus d epsilon 1 raised to n into exponential minus of epsilon 1 plus d epsilon 1. So, this is equation number 3. Okay. So, this is for the case of imperfect strip and this is the case for, that means at this section this right hand side is true, whereas for this section where the perfect strip is there, this one is true. Okay. So, this is the thing. So, if you look at the load versus strain curve, okay, if you just plot this load versus strain curve for the two sections, when your load is coming, maybe one it will come like this. Okay. This is for the uniform region. This is perfect region, we are calling it as uniform area, uniform region. Whereas for this part, it will be in an imperfect region, you will find that, okay, it is something like this. See, what happens is that load increases and at some point here, say, let me just say it as G, for the maximum load, and the maximum load which can reach, that is the maximum load which can be taken by the piece at any point. So, that will be this value corresponding to this, whatever you are getting is the maximum load. So, but because here this is a cross sectional area, when it reaches the maximum load, no, it will be there. So, that corresponding to that on your perfect crystal, it will be, you will have a strain of epsilon 1 u, which will be less than the strain corresponding to this on your reduced cross sectional area. That strain will be corresponding to your n. Okay. So, this will be epsilon 1 plus d epsilon 1. So, when that value reaches this n, it is so your maximum load can be this P max, because in your perfect strip or uniform region the cross section is very large, it will not go beyond this. Rather, in this region, when the stress reaches, the stress corresponding to this maximum load reaches here, it will start deforming, and that will be the strain which you will be showing as epsilon plus d epsilon 1 here. Whereas that corresponding to that external load, your strain in the uniform region will only be epsilon 1 u. We are just defining it as epsilon 1 u, maybe u should be the suffix, okay, I am just putting like that. That is maximum load. U corresponds to maximum load in that. So, that is the thing, generally the notation which is used. So, the strain in the imperfection corresponding to this maximum load, okay. So, corresponding to P max strain in the imperfection is equal to epsilon 1 plus d epsilon 1, okay, and that will be equal to n, because epsilon star, since epsilon star is equal to n, we previously got. So, that should be corresponding to your n, but that n value it will never reach for your perfect crystal, okay. So, that means in the uniform region, the load corresponds to only G, where your strain, the strain epsilon 1 u is less than your n, okay. So, it will never reach that value. So, whatever you are trying to apply the load, the deformation will take place at the imperfect region. So, this is the maximum uniform. So, you will find that this is always less than this your value of n, okay, because the load cannot go beyond that. So, this is the maximum uniform strain since it is measured in the uniform region of the test. So, uniform region cannot be loaded to a load more than G. Since any attempt to load beyond G, it will be transmitted to the imperfection, and the region at the imperfection only will get strained, okay. It will deform there, and finally in an uncontrolled way it will go, instability will set in, and then the material will fail there. Since all the tension strips which contain any of the tension strips you take, any strips where you are in real material when you are taking, it will contain some sort of imperfection. There is no doubt in that. You cannot tell that a material is there without any imperfection. Maybe that dA may be very small, that is all. So, but in that case it contains large number of imperfection in real materials. So, the greatest imperfection will become the site for the diffuse neck, that is where. So, wherever that an imperfection is there and the cross sectional area is the minimum, that will be the site for the diffuse neck. And once the maximum load carrying capacity is reached in the neck region, instability will set in. The material at the imperfection region, it will just start expanding or growing, and then finally it will result in the failure like tearing and other things. So, the difference between the maximum load in the uniform region of an imperfect strip and the strain epsilon 1 is equal to n at the maximum load in a perfect strip can be determined. So, that means, so what I said is now it is the difference between the maximum load or load maximum in the uniform region of a perfect strip and the strain where epsilon 1 is equal to n at a maximum load imperfect of an imperfect strip. In a perfect strip, that can be determined. So that can be determined by substituting epsilon 1 plus d epsilon 1 is equal to n in the imperfection side of equation 3 and epsilon u for strain in the uniform region. So that we can find it out epsilon u by n raised to n into exponential n minus epsilon u is equal to 1 plus d a naught by a naught. Okay. So in this real case, this n minus epsilon u and d a naught by a naught are very small quantities. So if you are just expanding this in the series expansion and taking the first term, you can get this relationship, that is n minus epsilon u is almost equivalent to say minus n into d a naught by a naught. Equation number 4. Now let us look at what happens to the strain rate sensitivity. So the effect of strain rate sensitivity. In the initial lectures we have discussed that the strain rate sensitivity is very important in bulk deformation of material at higher temperature, because at higher temperature it becomes more of a strain rate sensitive. Okay. So at higher temperature for deformation processing this is very important. Whereas in the case of sheet metal forming, even at room temperature also, though you may feel that strain rate sensitivity is not coming into picture, but depending upon the strain rate sensitivity of the material, that has an influence on your defect growth, okay, or maybe the strain to failure and how fast it reaches. That has an important influence. So let us look at that. So in normal strain rate sensitivity, that expression for the flow stress, so maybe for uniaxial strain, so that can be written as B epsilon dot 1 raised to n m, okay, where epsilon dot 1 is equal to d epsilon by dt, and that is equal to d L by L by dt. So that we can say it is equal to V by T, where V is the cross head speed, cross head or ram speed, cross head speed. Okay. So it depends upon, if you wanted to have a constant strain rate, this is the expression which one has to get it. And the forces, when you are transmitting it across these two sections, we can still write it as P is equal to sigma 1A. So is equal to sigma 1 d sigma 1 into A plus dA. So this will be for an imperfect crystal, and this will be for an imperfect strip, and this is for a perfect strip. or maybe this will be for the uniform region. Okay. So, this is the case. So, from this now we can write it as d sigma 1 so load is the maximum load. So, d sigma 1 by sigma 1 is equal to minus dA by A. That is the difference between the stresses in the uniform region and the region where imperfection is there. So, that is what we are getting it. So, now from this relationship, if I just put it as what let me put it as equation number A. Okay. So, from A you substitute it into this, taking the derivative and other things, we can get it as d epsilon dot 1 by epsilon dot 1 is equal to 1 by m into d sigma 1 by sigma 1. From this, if you take the derivative, okay, differentiating, yeah, we will get this relationship. Okay. So, that is equal to, because d sigma 1 by d 1 is equal to minus dA by A. So, minus 1 by m into dA by A. So, this we can get it as 5, equation number 5. Now, in this, if you really look at it, the difference for a given imperfection, the difference in the strain rate, that is a d epsilon dot 1, between the imperfection, the region of imperfection and the uniform region. So, you will find that that is d epsilon dot 1 is inversely proportional to the strain rate sensitivity index. Okay. So, that is rate sensitivity index, no, that is one. So, it is inversely proportional. That means, if you have at room temperature, if m is very small and the difference in the strain rate is very large, then the imperfection will grow very rapidly. Okay. So, that is the thing. So, if you are doing it at a very high strain rate and at a low strain rate, and the m is a material property. So, if m is small, then necking will take place at a much faster rate. The difference in the cross sectional area, strain, will be much higher. So, failure will localized necking will take place and it can fail. But in certain cases like superplastic deformation, where you can elongate it to maybe 500 or 1000 times or more than that. In certain cases, you have obtained even up to 4000 also, superplastic. If you just take a glass rod and heat it at a higher temperature and then you try to pull it, you will find that the elongation is very large. So, that is a typical case of a superplastic deformation. That is why in glasses, you can use this glass blowing to obtain a very large shape and other things. So, in metals also, in ceramics also, this type of phenomena is observed. So, where in such case, so in superplastic materials, under that conditions of deformation, superplastic material, say m is high, that is more than 0.3, that is it is high. So, in such case, you can just deform to a very large extent. So, m strain rate sensitivity even at room temperature also, if the m value is less, then it cannot deform much, okay, because necking will take place. But if m value is high, even at room temperature also, you will find that you can have a more strain or higher strain. Now, let us look at the next case, that is tensile instability in stretching a continuous sheet. Stretching a continuous sheet. Okay. So, in a tensile strip, if an imperfection is not there, is not present, or it is not existing, then diffuse necking will start when the load reaches a maximum value. So, when the maximum load is reached, the diffuse necking will place. So, in case of a sheet stretched over a punch, this diffuse necking is not generally observed in practical case. Okay. So, the tension may reach a maximum, but the geometry of the punch, why it is not happening is that the geometry of the punch, because on one side you are coming in contact with that. So, geometry of the punch, that it imposes constraint on the strain distribution. So, the constraint by the due to the geometry of the punch, you will find that okay, this diffuse necking is not taking place. So, by theoretically you may find that it can take place, but when it is just when it is stretched over a punch, that is not taking place. Okay. So, in a continuous sheet, development of the local necking are observed, which are similar to that occur within a diffused neck of a tensile sample. So, when it is a continuous sheet, this happens. So, width of this local necking which occurs is almost equal to the sheet thickness. So, you can see that depending upon the sheet thickness, more or less equal to that thickness will be coming. Okay, that width of this, because as I have mentioned, localized necking means that like a band it is forming, the width of that band will be equal to your thickness of the sheet. Though they do not contribute to the local necking, they result in tearing of the material. So, global necking is your diffused necking. Diffused necking will be more or less, the width of the local necking will be almost about the sheet thickness. Okay? And they do not contribute to the global necking. They result in tearing of the sheet. That is what. So, let us consider the condition for that, when this can happen. Okay? So, how these things are formed. So, we can consider a sheet deforming uniformly in a proportional process. Okay? So, like suppose you have a sheet like this, with a thickness T, and this is your tension T1, and this is your T2, this is your thickness T. Okay. So, if you just consider a unit size, where this is equal to one and this is equal to 1. Okay. So, in such case, you are assuming a proportional loading, deforming uniformly in a proportional process. Proportional process means your alpha and beta are remaining constant. The stress ratio and the strain ratio, they are remaining constant. So, if you look at, I just take a small element from that in this case, okay, and look at the stresses and stresses, sigma 1, this is sigma 1 and this is sigma 2, this is sigma 2 and sigma, this one will be 0, sigma 3 will be 0. Okay. So, this is the condition. So, the deformation in such case can be specified as one is stress conditions. If you take, there are the stresses are sigma 1, then sigma 2 is equal to alpha sigma 1 and sigma 3 is equal to 0, because it is a very thin sheet, we are assuming the stress across the thickness is 0. Whereas the strains are sigma epsilon 1, then epsilon 2 is equal to beta into epsilon 1, and the third epsilon 3 along the axis 3. So, that will be is equal to minus, which we have earlier itself we have described it, is equal to minus of 1 plus beta into epsilon 1. So, if you know that epsilon 1 and sigma 1, then you can always describe this condition. So, the principal tension in the sheet are the principal tensions tensions are T1 is equal to say sigma 1 into T and T2 is equal to alpha into T1 and that is equal to sigma 2 into T, because sigma 1 and sigma 2 are there. So, we can write this. So, maybe this we can write it as equation 6, this is equation 7 if you write like this. Okay. So, these are the state of stresses in this sheet. Okay. So, the condition for local necking, in this condition, under these circumstances, what are the conditions for local necking? The conditions which have been postulated is that local necking will start when the major tension reach a maximum. And see, in this condition, since it is a proportional loading, alpha and beta remains constant. So, the local necking will start when the major principal tension reach a maximum value. So, that means by equation number 7, T1 should be the maximum, or we can say if you take dT1 by T1 is equal to d sigma 1 by sigma 1 plus dt by t. So, that we can write it as dt by t is equal to epsilon d epsilon 3. So, d sigma 1 by sigma 1 plus d epsilon 3 we can write. So, this can also be written as d sigma 1 by sigma 1, because epsilon 3 is this, okay, into minus 1 plus b into epsilon 1. Okay. This is equation number 8. Now, when the tension reaches a maximum, that means derivative of that should be maximum condition, it should be equal to 0. So, that means so for the maximum tension, dT1 by T1 should be equal to 0. So, that means from equation 8 we can reach, if this is equal to d sigma 1 by sigma 1 is equal to this is d epsilon 1, sorry. Okay. So, if you bring that to d epsilon 1 to the left side, we can say that 1 by sigma 1 into d sigma 1 by d epsilon 1 is equal to 1 plus beta. And this is true for beta greater than minus 1. The strain ratio should be greater than minus 1. Okay. So, if beta is less than minus 1, so what will happen is the sheet will start thickening. So, if beta is less than minus 1, the sheet will thicken. So, because that is the ratio between sigma 2 and sigma 1. If it is less than minus 1, naturally it will be, strain will be, whatever, it will start, thickness will start increasing. That is the thing. So, and for a strain hardening material, the tension will not reach a maximum for a will not reach a maximum strain. Okay. So, in such case, where this beta is less than 1, since the sheet keeps on, thickness keeps on increasing due to a strain, due to the loading, it will never reach the value of sigma 1, because the stress inside that material will not increase. That is the main thing. So, for a generalized flow stress, when you are having, we can have a generalized flow stress relationship. Generalized stress strain relationship is the effective stress, we can write it is equal to your uniaxial flow stress is equal to K into effective strain raised to N. So, if you just substitute the value of effective stress and effective strain from our previous derived equation and other things, so this equation 10 will get the form of, so it will, that means that sigma bar is equal to say square root of sigma 1 square minus sigma 1 sigma 2 minus sigma 2 square, or you can say 1 minus alpha plus alpha square into sigma 1, root of 1 minus alpha plus alpha square into sigma 1, or similarly epsilon bar, it is root of 2 by 3 into epsilon 1 square plus epsilon 2 square plus epsilon 3 square, or we can say root under root 2 by 9 into epsilon 1 minus epsilon 2 square. So, that relationship if you substitute and then get it, we can get this in this form, sigma 1 is equal to K dash into epsilon 1 raised to N. Okay. In this is the condition when you are having a proportional loading, where alpha and beta remains constants, K dash is a material property and is a constant calculated from K, N, alpha and beta. Okay. We are just determining from the value of K and alpha and beta, from that if you are getting. So, if you differentiate this equation 1, we can write this 1 by sigma 1 into d sigma 1 by d epsilon 1. So, that will be equal to N by epsilon 1. Okay. So, for the maximum tension, if you are substituting this in the previous equation number 9, so substituting in equation number 9, 1 by sigma 1 into d sigma 1 by d epsilon 1 is equal to 1 plus beta. Okay. So, that is equal to N by, so now this is the maximum case, when you are writing it epsilon 1 star. Star always refers to the case for maximum load condition. Okay. So, that it implies that epsilon 1 star is equal to N by, you are bringing 1 plus beta. So, if you know the value of beta and if you know the value of N, the maximum strain along the principal direction 1 we can determine, and also along epsilon 2 star is equal to beta into N by 1 plus beta. So, these two relationships you are getting. So, the strain at maximum at maximum tension, that is epsilon 1 star plus epsilon 2 star is equal to N, you are getting. So, this value, if you consider this epsilon 1 star and epsilon star, the maximum strain in these two directions, the sum of that should be equal to N. That means epsilon 2 star is equal to 0, epsilon 1 star is equal to N. That means for a uniaxial tension testing, you will find the maximum strain is equal to n. But for biaxial and other conditions under different strain paths, the total value should be equal to n. So, let us see these two conditions. Okay. So, in a tensile test, when you look at it, for a tensile test, beta is equal to -1. We have earlier discussed about tensile test, beta is equal to -1. Hence, the maximum tension occurs. Hence, maximum tension occurs when 1 by sigma 1 d sigma 1 by d epsilon 1 is equal to 1 by 2. Okay. So, that is equal to n by epsilon 1, or that indicates that in such a case epsilon star is equal to 2n. This is a very important point, one has to look at it. So, in the maximum tension condition, it signifies that the onset of local necking, that means the local necking strain in a uniaxial tension is epsilon 1 star is equal to 2n, which is twice the strain for a maximum load and start of diffuse necking. So, for a uniaxial tension, it is twice the strain for a maximum load and where the start of diffuse necking takes place. So, that is the condition which is coming. Okay. So, you have to find out in this particular case, you will find that in sheet metal operation, you may get a strain which is much higher. So, you are going to get it at a 2n and other things. So, by drawing say grid circles on a sheet, this is how the sheet metal experiments are done. You make, because I think in this module itself, lecture number 2, if I am right, that grid circles I have demonstrated. So, if you are drawing this grid circle, we can experimentally determine the strain at the onset of local marking, because under different conditions it is straining. So, strain history at different places may be different. Okay. So, there we can study the minor and major axis of your ellipse and then find out what is the strain along epsilon 1 and epsilon 2. So, we have discussed that. Maybe during if it is a circular grid, it may just extend like this, like an ellipse. So, you measure this and this. So, after this, so wherever the failure has taken place, adjacent to that you measure that. You may not be able to find it exactly at that split, but very adjacent to that you measure the strains. Okay. So, that will be because that is the region very adjacent to a local necking. So, we can approximate that is the region where the maximum straining has taken place or very near to that. So, and in a similar way, you measure these strains for different strain paths, because you can always, by measuring the circular this one, you can measure the strain path at different places, and in both the quadrants of a strain diagram, okay, we can establish a foaming limit diagram. So, after measuring this for different strain paths in quadrant 1 and quadrant 2 of the strain diagram, we can just look at what is called as a foaming limit diagram, which delineates the boundary of uniform deformation and onset of necking. So, the point which you are going to get it very adjacent to the failure, or even some means if you can measure at the failed region also, the minor and major axis if you can measure, though it is very difficult, at least that point you know that okay, this is the boundary between the for the strain path, particular strain path with epsilon 1 and epsilon 2 combination of that, this is the region where the failure will take place. So, at different places if you measure it and then you plot all these things, you can just get a two region, one where the failure can take place and the other where failure cannot be closed. The boundary between that is the safe region. So, that we can get it. So, this is called as the forming limit diagram. Okay. So, that if you look at it, it will be something like this. So, this is for your epsilon 2, this is for epsilon 1, and you will find that this is for 0. So, this is a continuous sheet. And you will find that you can just draw this maximum tension line like this for a combination of epsilon 1 and epsilon, maximum tension line. The maximum tension line will intersect it at the value of n. And if you just join this, maybe for any condition, no, you can just draw this for any condition. So, that means this you will find that the slope is 1.5 here. Okay. So, whereas for the actual case, so in the second quadrant, no, it's okay, you are finding it safe, but if you look at the actual case for real material, you will find that in the first quadrant it is not so. Okay. Here you are getting up to here it is true, up to this is up to n value, this is epsilon 1 and this is epsilon 2, but here instead of directly coming like this, so you will find that it is coming something like this. So, there is a region here where it is not matching. So, this is the value of n. So, in this case when you look at it for materials with the same value of n, the following observations can be made. One is the for same value of n, the strain path in the second quadrant, that is, this is the second quadrant here, this is the second quadrant, the strain path in the second quadrant is that is for beta is equal to less than 1, the experimental FLC is coinciding with the maximum tension line. The strain path in quadrant 2 that is for beta less than 0, the experimental FLC, that is where FLC is equal to forming limit curve. Is coinciding with the maximum tension line. Okay. Whereas for both the epsilon 1 and epsilon 2 positive, that is in the biaxial stretching, that is in quadrant 1, epsilon 1, sorry, not sigma, epsilon 1 and epsilon 2 are positive and beta greater than 0. This experimental forming limit curve or FLC, it do not follow the maximum tension line. That is what you can see here. See here, it is not following the tension line, but maximum tension line is this dashed line. But you will find that it is at a higher value. Okay. So, that means this indicates that there is some process which retards the necking in the biaxial tension condition. The biaxial stretching condition, there is some reason which retards or which slows down the necking process after it has reached the maximum tension line. So, that is one thing. So, how that is taking place, we will have to look at it. So, let us, for that particular case, let us just assume a case in a material, say a sheet like this. Let us assume that the necking is taking place along this region. So, whereas this is your sigma 1 and this is your sigma 2. And if I just take a section along this cross section area, you may find that, okay, just do like this. This is the section, if you just take, it's a reduced section, that necking has taken place, and if you just look at this as y and this as x, the local coordinates axis, if you take like that, and see if this is inclined at theta, okay. So, we identify the uniform region as A and an imperfection as B. So, that means this region as A and maybe this region as B, if you identify that. For analysis of the necking process, the assumptions are, if you just consider the assumptions, one, the stress and strain ratios remain constant, alpha and beta are constant before and after and during necking process. Second assumption is, for necking process to be local, the necking process should not affect the boundary conditions. Okay? The necking process, for the process to be local, the necking process should not affect the boundary conditions. Okay. That is the strain increment in both the region A and B along the y direction, that must be 0. That is, the strain increment along y direction, that is along the groove, if you assume it is a groove, along that groove, in that direction, y direction, in both A and B region must be 0. It is going to be the same. Okay. So, from a Mohr circle representation, now we can just draw the Mohr circle representation for the state of stress in this case and the strain in this case, sorry, the strain and d gamma. If you just find out this is a circle will come like this, okay, and this is the center. So center we can just write this as 2 theta, okay, and this is 1, this is 2. So beta d epsilon 1 and this is equal to d epsilon 1. So this is the, so from this Mohr circle we can find that center of the circle. So this is equal to 1 plus beta by 2 d epsilon 1, that is center of the Mohr circle is equal to is at 1 plus beta by 2 into d epsilon 1, and the radius of the circle, from this itself radius of circle is 1 minus beta by 2 into d epsilon 1. So the direction of 0 extension d epsilon y is equal to 0. So that you can get it from the circle, okay. So that the direction of 0 extension that is d epsilon y is equal to 0 is given by cos 2 theta is equal to 1 plus beta by 1 minus beta. We are getting equation number 13, okay. From this what we are getting for a uniaxial tension, so beta is equal to minus half for beta is equal to minus half, hence theta is equal to 55 degree, okay. So for a plane strain condition beta is equal to 0. For plane strain condition beta is equal to 0, so theta is equal to 90 degree. So that is perpendicular to the principal stress, that is maximum principal stress, okay. And if beta is greater than 0, there is no direction in which extension in which the extension is 0. This is the thing. There is no direction in which extension is 0. So that is from this we can get that, okay. So if there is a direction in which there is no extension, then local necking along this direction is possible when the tension reaches a maximum, okay. If there is no direction of 0 extension, that is by a stretching process where beta is greater than 0, the strain at which tension is maximum is given by, earlier we found that it is given by epsilon 1 star plus epsilon 2 star is equal to n. So that is it. So that means if there is no direction of 0 extension, that happens when beta is greater than 0, okay, for the stretching, biaxial stretching process. Strain at which tension is maximum is given by this one. However, geometric constraint permits prevents the instantaneous growth of the local neck. So, in this previous figure, if the line shows maximum tension in both quadrants, but only indicate local strain in the second quadrant, where minor strain is epsilon 2 is negative. So, also for plane strain beta is equal to 0 and epsilon 2 is equal to 0 for the plane strain condition, the major strain at necking is the minimum. This is the condition where you are getting. Okay. Now, if you look at for a biaxial tension, necking and biaxial tension, so in the strain diagram, we found that for epsilon 1 and epsilon 2 both are positive, there is no 0 extension in the first quadrant, that is for beta is greater than 0. However, when you do the experiment, still necking occurs under biaxial tension. So, though in the strain diagram, there is no 0 extension in the first quadrant. First quadrant means, see, this is greater than 0. Okay. Experiment shows necking under biaxial stress. So, at a strain greater than the attainment of maximum tension along a line perpendicular to a major tensile axis. So, this experiment shows necking under a biaxial tension occurring one at a strain greater than that of the attainment of tensile axis and along a line perpendicular to the major tensile axis. So, that if you look at, if you just consider this the figure below here, if you just consider a figure like this. So, this is your sigma 1, and say maybe this is sigma 2, and if you take a region where there is a imperfection, say area, this is the uniform region and B is the imperfection region, this is the uniform region. So, we can say that B is the imperfection region and A is the uniform region. And if you assume that an imperfection as a groove shown by this dashed line with a thickness Tb. So, if I just take the cross section of that, this is Ta and this is Tb. Okay, with these two cross section, and So, this imperfection, see, it is very difficult to characterize an imperfection, but let us assume that imperfection is characterized by a homogeneity factor given by F0, which is equal to TB by TA at the initial case, okay, at 0. And this normally, typically we can assume that F0 is of the order of 0.001. That also we can assume. So, when you are loading it, strain in the region B parallel to the groove would be constrained by the uniform region A, so that the compatibility condition sigma 2B is equal to sigma 2A. So, strain in region B parallel to the groove will be constrained by uniform region. So, that now we can say sigma 2B is equal to sigma 2A, which is parallel to the groove. That is one thing. So, in that case now we can just assume that the proportionality condition, if it is there, we can say sigma 1A is the, and sigma 2A, which is equal to alpha 0 into sigma 1A, and the third is sigma 3A is equal to 0. Now, the strain epsilon 1A, another is epsilon 2A is equal to beta naught into epsilon 1A, and epsilon 3A is equal to minus of 1 plus beta. This not represent the initial condition epsilon 1A. So, we can write this as 16. Okay. But the case is not true when you are loading it in this direction 1. This is your direction 1 and this is your direction 2. So, this is 1 and this is 2. So, when you are loading it in the direction 1, the strain will be different in both the place, stresses also will be different. Okay. So, the same tension in direction 1 is transmitted across the region, both the region. So, that the same tension is directed in direction 1 is transmitted across the region such that T1 is equal to sigma 1A into TA, and that should be equal to sigma 1B into TB. So, stress will be different in both cases, and TB by TA is equal to, you will get it as from this, TB by TA is sigma 1A by sigma 1B. So, that it comes TA by TB is equal to F, no? So, you get it as question number 17. So, if you consider the initial yielding, no, if you just consider the stress diagram, if this is sigma 2 and this is sigma 1, and if this is your yield locus, you may get it here. Okay. This will correspond to your sigma 1. Okay. So, here it is equal to 1 by alpha naught, and this point if you give it as A0, this is a uniaxial stress is equal to sigma 0 if you put it here. Then on loading, the groove will first reach the yield. So, groove is going to reach first the yield. Okay. So, that means in this condition, so from 17 you can get it as, so in the uniaxial yields, if uniaxial yield strength is sigma naught on loading, groove will first reach the yield surface because their cross section area is less. So that means from 17, equation number 17, what we will find is sigma 1b is greater than sigma 1a for f less than 1. So that is what. So since sigma 2a is equal to sigma 2b in both the case, material in the groove cannot deform. That was a constraint condition due to geometric constraint. So that is what happens. Since, so you will find that, so this is your B naught and here it is 1 by alpha and this will be your sigma 1b. Your stress in sigma 1b will be much higher than in sigma 1a. So that is what it is coming. So you will find that this one this slope also is changes. Okay. So since sigma 2a is equal to sigma 2b, the material in the groove cannot deform due to material constraint. Therefore, as the stress in A increase to reach the yield locus, when the stress in the A increase to reach the yield locus, the point representing B, okay, will move around the yield stress, yield locus to B naught. So that means when this in area in the region A, where there, which is a uniform region, when the stress is trying to reach the yield locus, which is represented by A, since the cross sectional area in region B, which contains the imperfection, so it will reach the value of B. So that means it has to just rotate. Okay, it will move around the yield locus to B naught. So if you just consider the incremental deformation which is taking place, this is your d epsilon A, which is normal to your locus. This is A0. And maybe we are just finding it, okay, it is something like this, okay. And maybe here, this is d epsilon B, which is B naught here. Maybe this has to be normal to this, okay. So let me just draw like this. So that is, this is 1 by alpha, slope is 1 by alpha, and this is 1 by alpha naught. You are getting this. So this is the strain field which you are getting, d epsilon B and d epsilon B. So if you consider the increment in the deformation, no, see epsilon 2a is equal to epsilon 2b. The increments parallel to the groove is the same, that is strain increment parallel to the groove is same, that is true. So we can see that strain vectors are perpendicular to yield surface in this case. Since each region is deforming with a different strain rate, so you will find that both the regions are deforming with a different strain rate, the strain ratio, not strain rate. The strain vector for the groove has rotated to the left. So since each region is deforming with a different strain ratio strain vector for the groove has rotated to the left, and for strain increment parallel to the groove. Whereas the strain increment across the groove this is will be greater in the imperfection than in the uniform region. So, if you just draw that part, you will find that in this if this is d epsilon 2 d epsilon 1 a and this is equal to d epsilon 1 b. So, this is 1 by b naught beta naught and this is equal to 1 by b 1 by beta. So, this is what you are going to get the strain. So, you will see that in such a condition inhomogeneity will be greater, that is the F will diminish. That means you will find that d epsilon 1 b is greater than d epsilon 1 a. The strain in the groove will increase, because basically if you really look at it, cross sectional area is just that. So, strain in the groove will increase compared to that in the uniform region, and only slightly when the tension is increasing. See, when you increase the tension, you will find that it is increasing very slightly only. So, if you just really look at that, in this condition, when you do that, see, if it is like this, you have A naught the stress field, it will move like this, and this is your this one. So, when as the tension is increasing slightly, you will find that it is increasing and the strain is increasing. So, if you just draw like this, if this is the case of epsilon 2 a 1 b and this is epsilon 1 a star, I will just draw like this. In region A and B, how the strains are taking, how the stresses are happening. So, you will find that at some area it slowly increases slightly, and then after some time, no, it just keeps on increasing and reaches this value. Okay. So, this is the point for B, and this is for the case for A. The strain field is like this. Okay. So, strain in the groove, it will increase compared to that in the uniform region only slightly when the tension is increasing. Okay? When the tension is increasing, it will increase slightly. Gradually, it increases after the tension maximum has reached, and then continues till the groove reaches a state of plane strain, that is at BF. That is, once it reaches here BF, it reaches a state of plane strain. At this stage, the strain parallel to the groove stops. So, that is what is happening. And the groove will then continue until failure and the strain is uniform. In the uniform region, it ceases. So, that is what happens at this. The strain state just outside the neck is the maximum strain that can be achieved. And the strain epsilon 1 star A and epsilon 1 star B are known as the limit strains. The analysis is repeated for different values of alpha naught and beta naught, and a diagram for biaxial strain region can be established for this case. So, if you do some experiments like this by doing for different strain history and other things, and plot this epsilon 2 and epsilon 1, you will get this forming limit curve. Okay. So, when this is 0, this is epsilon 1, this is epsilon 2. So, depending upon this, this is n. Okay. So, here it is minus 1, it is plus 1. So, in actual case what happened, it is instead of going that maximum tensile strain, it follows this path. So, this may be your experimental things for different strain paths, you can just get it and you will get this part. So, this is the forming limit curve. So, in this what happens is that this gives, it delineates the region between area where deformation is taking place. So, here it is a failed region, whereas this is a sound region. If your deformation, the combination of stress and say epsilon 1 and epsilon 2 is within this this boundary, which is shown by this line, shaded line. So, that is safe. The other region, once you crosses any of the strain, it is higher, then it will fail. So, once you have for a particular material this forming limit curve is there, if you know the value of n and then you get this, then you can always restrict your deformation to such a value that the strain in the sheet is not approaching this limit curve bounded by this region. So, that is what is coming. So, in the second quadrant, if it is there, you can always tell the limit is always on the maximum tension line, whereas in the biaxial stretching, you will find that it is not so. You have a better, more value a region you are getting it. It is not, otherwise no, it should have come like this. Okay, but here you are getting higher. You will get a higher strain in this case. But only thing is, what is the maximum strain you can get as a combination of epsilon 1 and epsilon 2. So, that limit should not be crossed. That is the advantage of using this. Now, if you look at what are the factors affecting the forming limit curve, the two important factors, there are many factors, but the most important factors are, one is the strain hardening. So, if you look at that strain hardening n, the strain hardening say like this is your 0 and it is this. When you are having a low strain hardening value, it is like this. Okay, maybe it will be drawn properly. So, for low strain hardening value, you will find it is like this. So, this is N1, whereas for high strain hardening material, you will have still higher value. So, this is N2, where N2 is greater than N1. So, for biaxial stretching, high N value is required, so that you have a large amount of strain which you can get it. So, the material should have high N value, work hardening exponent, it should be higher. So, if you are having a material having low work hardening exponent, then for biaxial stretching it will create problem and then tearing will take place. Okay. So, when n is equal to 0, the plane strain forming limit along vertical axis, that will be 0. but it can be stretched in fully biaxial stretching. That is the biggest advance. So, in plane strain condition it may be difficult, but in biaxial stretching you can always deform to a very large extent. Another is the rate sensitivity. If you have say rate sensitivity also, so this is for one case and the other case is like this. So, you have a larger area. So, this is high say M1, M2, M1, okay, I will follow the same order. M1, M2. So, M1, M2 is greater than M1. In that case also you will have. So, in biaxial stretching this M will delay the growth of the neck. Higher M value will delay the growth of the neck. That is one advantage with the high strain rate sensitivity material. Okay. There are other factors also, but see like the other factors are you cannot characterize what is called as a this defect. It is very difficult to characterize, or imperfection. You cannot characterize it properly. Then failure of the material because it gets work hardened, that also is very difficult to use in these cases. Okay, with this today it is over.